So just a few words about this large-scale facility. So probably you have already heard it, that the normal way to access the experiments is through proposals. So we need to, or you need to write like some more or less meaningful proposals to formulate the problem and to show that it is feasible, to show that it has sense to touch these materials, your materials, by our techniques, small angle scattering in particular. Okay, somebody wants to introduce yourself, Janaki, for example. Hi, Janaki. No mic should be turned on.
Yes. I'm sorry for the mistake.
Mm.
I'm Janaki Devi, and I'm a first-year PhD student in the Department of Inorganic Chemistry. And I work specifically with polyoxometallites.
Polyoxometallites. Okay. What kind of experimental tools?
Yes. Vanadium, especially on vanadium-based poly. Actually, we use the X-ray diffraction methods, but I have not
this point. So I prepared an introductory PowerPoint presentation first. So let me tell you how this meeting will be scheduled. So first we shall describe, probably again for the second or third time, some key facts about small angle scattering. Then we will see how the experiments, how the measurements are done, with some video, again, video tutorial or video demonstrations. And the last one will be to make some data analysis on data which are already recorded or measured at different instruments. So this we will do by using the software what you probably have downloaded, or if not, then it can be done within a minute if you have not done it. So let me share the screen. Screen share works like that. I'm sharing this presentation right now. Trying to press the F5, which works. So we shall see some basics of the small angle neutron scattering. So this presentation was prepared by my colleague Adele and by myself, and it is not to repeat what you have already heard, but just to re-emphasize the important things which must be remembered. So the first slide is about diffraction methods in general. So how do we classify the diffraction methods? First is now we talk only about neutron diffraction. So the first thing is the elastic diffraction. I don't know. Opa. The first thing is the first field is the elastic scattering, and within elastic scattering there are a few subfields, which one of them is the small angle scattering, which can be done as you see here in the brackets by different types of instruments. The most standard one is the pinhole. It's so-called pinhole small angle scattering diffractometer. The TUF, it stands for time of flight. So this works mostly for, this is a higher resolution method, and this measures the speed of the neutrons, and it provides a higher resolution in terms of energy. And then finally, the third kind of instruments is the double crystal focusing. So this is a really high precision instrument. But on the other hand, it has very low intensity, so it should be used, or it can be used only for specific purposes. Now, if we look at the diffraction not under small angles, but under wide angles, then we have the wide angle scattering for liquids or amorphous materials. This means that we see the scattering at angles which are larger than, say, 5 or 10 degrees and go until the maximum. The maximum is approximately 180 degrees. So it's almost backscattering. So here we can see the interatomic distances between the molecules and between the atoms. And if the system is not crystalline, that is, if it is liquid or if it is amorphous, then the scattering patterns they contain information, but it's not so easy to extract the information from them because there are no distinct peaks, there are only waves. So this is another field. Probably more familiar for everyone is the wide-angle scattering in crystalline materials, which is usually called diffraction. And this is the same as the X-ray diffraction. So here again, we use neutrons and we measure peaks, and these peaks, the positions of the peaks, they provide information about the distances between the atomic planes in the solid material. Now, just again, a few words about the inelastic scattering. In inelastic scattering, we analyze the exchange of the energy between the neutron and between the atom. And this is very distinct from the X-ray scattering, because in X-ray scattering, it doesn't happen. And there are 3 typical methods, which are the spin echo, neutron spectroscopy, the quasi-elastic scattering, and the triple axis spectroscopy. So we are not talking about these things today. So let's see what we will be talking. So first, a few remarks. So this is already like undergoing. Then only a little bit of theory, which includes the most important thing which is needed for small angle scattering, and this is the notion of the contrast between the different components of the sample. Then we shall see that what do actually we measure. We measure the intensity of the scattered neutrons, and we measure them by the detector, and there are a few experimental or technical aspects which must be known for making a proper measurement. Now, instrumentation, it consists of a description of the basic or general type of small angle scattering instrument. And then we shall see how actually a measurement is being done, and in the end we shall train together with you online some examples for data analysis. Voila. Please ask questions if you have questions to any of these previous terms. And this is a slide. So this slide about a regular training school which we organize in Budapest. If you happen to be interested, then you can apply it probably in this year, late in this year, or next year, or after the next year. So this is a regular event, and it contains only neutron techniques. So you will find this information somewhere in the website. Let's go further. So the basic instrument of neutron scattering, at least in our neutron center, is the small angle scattering machine, and this big yellow tank is actually the small angle scattering diffractometer. It is called yellow submarine. We can probably not read it from this side, but we will see other pictures. So basically, it is a big tube evacuated. It contains a very, very low pressure. This is in order to not to let the neutrons go to the detector and without interacting, without scattering on the air. Now, some general fields, maybe one of your fields of interest would fall into one of these topics. If not, then I'm sorry, but still you can make some use of this introduction. So the small angle scattering means that the scattering comes to small angles, and this means that we are sensitive to sizes of the particles or sizes of the parts in the sample which are relatively big. This size means something between 1 nanometer, or structures between 2 nanometer up to 100 nanometer, or in certain cases up to micron sizes. So if you think that what kind of material can belong to this or can have structure in these sizes, then first of all we must remember the biological systems. So the most basic unit is the protein, probably for the cell, in the cell, and all proteins, they have a sizes approximately a few nanometers. So they perfectly fall into the domain of the small angle scattering and can be very well characterized. And this is one of the major topics of the small angle scattering. Here I wrote in the center, I wrote SANS and SACS because both these methods, they are sensitive to all these types of systems. Then polymers are long molecules. If they are not solid, but they are, for example, dissolved in solution, then they form entities or globules which are again of this interesting size between a few nanometers to hundreds of nanometers. Polymers can be inorganic polymers, for example, silica and silica gels, and the silica xerogels and aerogels are again it is structured at the nanometer length scale, and it can be very well studied by small angle scattering. Now in industry, people are interested in materials, in real materials like construction materials, like concrete or cement or wood, or in metals or metallic alloys, which can have which normally they are homogeneous, but in case they have some inclusions like precipitates or other phases, then this is again the object of small angle scattering to see it. Liquid crystals, so they are in front of us, yes, in the display. So they are layered materials which with interlayer distance is about 2 or 3 nanometers. So again, they fall perfectly to the domain of small angle scattering. The colloidal particles or nanoparticles, we shall see such examples in the practicals. So there are many types of them. The ceramics, it is a recent direction nowadays that people who work with archaeology, they try to identify either the origin of the artifacts or the way they were processed. And small angle scattering in particular can give some information about these methods of processing or parameters of processing of the ceramics. Now, the liquid systems are important for physical chemistry. For example, the micelles or all kinds of solutions of surface active molecules. But they also are very good model systems which can support the development of theory of liquid matter or theory of everything, of basic interactions. Now I mentioned the proteins in biology, so they are more or less globular things. But there are also another type of biological thing. These are the membranes, the cell membranes, for example, or the membranes what we can find in the green leaves, where the photosynthesizing mechanism is basically a set of or a couple of membranes. And the distances between the membranes are again a few nanometers, and they are again related to small angle scattering as the best method to characterize. So all these things in principle can be measured by other tools or techniques, first of all by electron microscopy, but it's important to remember that electron microscopy gives a static picture, and very often you need to process the sample, so it is not the native state of the sample very often, especially for biological or for liquid kind of systems. Let's go further. Just a scale or a picture about the characteristic size scale. So now here we see the 10 to -5 micrometer. This means basically subatomic or interatomic distances. So in this range, the crystallography works. Crystallography determines the structure of the molecules or the crystalline molecules. And if the molecules are in liquid state or amorphous, then again we can determine more or less the distances between the atoms and the molecules. Now the microstructure, which is exactly the domain of the small angle scattering, here we see the small angle neutron scattering, reflectivity, X-ray scattering, and X-ray reflectivity. So this is the size is between 1 nanometer and 100 nanometers. So the systems I have listed in the previous slide. And now there are some bigger objects like viruses, which are very popular now, or bacteria. So some parts of viruses can be entirely detected, or some parts of bacteria can also be detected by small angle scattering. But for them, mostly these use SANS, which is the ultra small angle scattering. So this needs a special instrumentation, a double crystal or a double band crystal as monochromator, but still this technique and all the formalism, it's the small angle scattering. Now, as you see here by these bars, so the transmission electron microscopy covers again all these ranges, and for big particles starting from viruses also optical microscopy can be used. So what is the basic? The basic is that in the theory that we have a neutron, which is a wave with a wave vector k is 0. Here is the sample, and the sample is scatters at certain angle, and we have a k vector k. And the difference between the initial and the final k vector is called the momentum transfer. And in the case of elastic scattering, so this momentum transfer basically is can be calculated from this triangle, assuming that both vectors have the same length. So it's only the scattering angle which determines the scattering vector. So probably you know this basic equation, which is the Bragg equation. It gives the relation between the angle of the scattered light and the angle of the neutron, and the d, which is the interplanar spacing. And this Bragg equation determines the positions of all the diffraction peaks in case of crystalline or half crystalline materials like liquid crystals. Now this is the wide angle scattering domain. In the small angle scattering domain, the curves, they look more featureless, I would say. So they don't have sharp peaks usually, but they have various parts of curvature which are not always easy to understand or call them without any analysis, and even data modeling can sometimes lead to ambiguous results. So we will see how it works in some real samples later. So probably the most simple thing in the theory is the particle. So this green box is a system of nanoparticles. So these nanoparticles can be either solid, so they can be colloidal nanoparticles, but they can also be fluid, so they can be micelles. You know, micelle is a small sphere composed of surfactant molecules. Normally they are fluid, so these spheres are not exactly spheres, but they are fluctuating or undulating spheres. But the average is usually either a sphere or an ellipsoid or a cylinder. So in all these cases, we can construct the scattering intensity. So this is called the macroscopic cross section, the sigma, and this can be taken as an integral of the scattering vector. Here is the scattering vector, and this is the distance between the scattering centers. So if we take this integral, then we come up with some formula which will tell us the shape of the scattering picture. There are two factors here. One is the contrast. Contrast is the density between the particle phase and between the matrix phase. So there are ways to improve this contrast, to vary this contrast, and this will be called contrast variation. And this factor is just for normalization. We don't deal with this now. So contrast variation. Contrast variation is important if we have not the simplest system. So if I go back now, so this is the sphere or spherical particle in a homogeneous matrix. So for this system, we don't need contrast variation. It's enough to have only one contrast, which will be strong enough to see the difference between the two phases. But suppose we have more complex particles like these, which are called core shell particles. So there is a core and there is usually some shell around them. Again, they can be either solid or solid with a soft or with a fluid shell, or they can be fluid inside and fluid outside. It means copolymer micelles or copolymer surfactants. So if we want to measure their structures, then we need to have more information. So we need to extract information about the sizes of both parts, and for this the contrast variation is especially useful. So by changing this contrast by isotopic substitution of one of the parts, then we can vary, we can make one of them constituents of the particle visible and the other we can hide. For example, in this case, we see only the shell. In this case, if these contrasts are different, then we see both the shell and both the core. And if we succeed to match the contrast of the matrix and the shell, then we can see only the core. If you are lucky, then we can do all these three types of contrast variations, but it's not always possible. But already by using two different contrasts, we have much more information, and this can be used for revealing the shape of the particle with a much better accuracy. Let's go next. For example, in these previous three systems, so these are model curves for small angle neutron scattering. So in case we see the shell or the shell and the core, we have these red and blue lines. We see that they have much less structure. However, this green line has a very well pronounced peak here and a very well pronounced minimum here. And this is characteristic for a single shell particle. So for the case when the density inside the particle and outside the particle are the same. So there are such particles, for example, protein shells, which are just shells, and there is water outside and water inside. And we shall see such a system in the last session. Now, we can compare the neutron scattering with X-ray scattering. In X-ray scattering, normally we don't have the possibility to vary the contrast, and that's why here we have only one curve, and this curve is a definite curve, so we cannot play with it. We cannot vary the contrast between the shell and the core and the solvent. So this means that the information what we can extract by small angle X-ray scattering in the case of such complex particles is definitely less than in case of neutrons. These are examples actually for water in oil microemulsion, which is a very thin shell made of surfactants, and they separate the inner droplets of water, and the outer phase is made of oil. Now let's come to the instrumentation. So this is the general view of a nuclear research reactor, a typical nuclear research reactor. So this building in the very center of this picture, this is the reactor itself, and inside the reactor we have the core of the reactor, which is roughly a ½ meter in diameter cube, or not cube but hexagon in this case, and it has many channels which are coming outwards from this central zone, and in these channels the neutrons which are emitted from the core, they are transferred to the instruments. So these orange blocks here, they are shieldings, and they cover the instruments. For each channel we have one special orange block here. This is an orange wall. Inside the orange wall we see a diffractometer. Probably some of you will have a practice on this diffractometer. And in this tunnel we have three neutron guides which go to the next building. They transfer neutrons to the next so-called experimental hall, where other instruments are situated. So this is the scheme of the instruments in the Budapest reactor. So here is the reactor core, and there are two instruments which are far away from the reactor. This one is the so-called time of flight diffractometer, and the second group of instruments is situated in this neighboring building, which is the experimental hall, and the small angle scattering diffractometer is also situated here in the very end of this black or red dotted line. This is the way of the path of the neutrons. So these are neutron guides here. There are a few more instruments like a reflectometer here, another small angle scattering instrument, and a prompt gamma irradiation station. Around the reactor there are some more instruments which are close to the reactor core, because in this case they use a higher intensity, but they don't use very well collimated beams, so they don't need it because of the optimization of the resolution. So this is a liquid diffractometer. This is an elastic scattering, inelastic diffractometer, a triple axis diffractometer, and the third one, I don't know if you see my cursor, but now I'm showing at the top of the picture in the left side. So the third instrument is a material testing diffractometer. It's called M-test. So these three instruments are conventional neutron diffractometers. Let's go to the next picture. I go back. We see the scheme. So there is the reactor core, Please tell me if you see my cursor or not.
Yes,
Otherwise,
we can see.
you can see. Okay, thanks.
Yes.
Very
And there are two questions in the chat. Do you want to reply now or after when you finish the presentation?
Actually, I would like to see, but I don't see the chat because my screen doesn't show it.
Okay.
I can make it visible.
Do you want that I read the questions or you want to do after?
Please read it. Maybe they are relevant to this first part.
Now, what kind of neutron sources are usually used? The first one. And the second one is, can SANS and SACS be used to study the polymer electrolytic membrane using the case of fuel cells?
Yeah, for the second one, the question is definitely yes. And there are many studies and many papers. So if you just search in Google, then you can certainly find. So usually the small angle scattering, SANS or SACS, it gives the organization of the polymer inside this membrane. And the first question was that what types of reactors?
What kind of neutron sources are usually used?
Well, the most common is the nuclear reactor. This is the traditional. But since now they are considered to be dangerous in some respect, now they are not being replaced, but new sources are being built, and they are continuous spallation sources, which means that there is no nuclear reaction which is so-called risky or dangerous, but the fission chamber is irradiated by an accelerator, by particles from an accelerator, and then they produce neutrons in the same way as the reactor. And such setup is called spallation source, and it is considered to be less risky because you can stop the accelerator at any moment, and then nothing will follow. So there will be no chain reaction. So basically, these are the two types of neutron sources which are used in neutron scattering. And there is a third one, which is probably unique, and it works only in Russia, in the Joint Institute of Nuclear Research, which is near Moscow. And that is a plutonium source which is rotating on a wheel. And this plutonium source gives impulses of neutrons at every rotation of the wheel. So it is somehow in between the continuous reactor source and the accelerator-based spallation source. I think this was your what you wanted. What was the question was about?
Yes, perfect.
Okay. So let's go to the next step, which is the instrumentation. So reactor is in the left, the instrument in the right, and in between there are the elements which are necessary for efficient transfer of the neutrons which are produced in the reactor, and they must reach the detector. The detector is this blue line here in the very right. So first of all, we have the reactor, which is a half circle here, and in the wall of the reactor we have a cold source. The cold source is an important device. It consists of a tank, of a half-liter tank of liquid hydrogen, and in this liquid hydrogen the neutrons are slowed down simply by mechanically. So they are slowed down. So they are colliding with the atoms of the cold hydrogen, and because the hydrogen is cold, then the neutrons also lose their velocity. So in the very end, they are cooled down to approximately 10 or 20 Kelvin. And this makes their velocity much slower and the wavelengths much higher. And this is beneficial for the purpose of the small angle scattering type of experiment, among others. So all the instruments which are situated in this guide hall or experimental hall, they are operating with these cooled neutrons, and all these instruments, they are optimized in a way that the cold neutrons are better for them. Either they give better resolution or they give higher intensity, or both. So these sections of these white sections, they are neutron guides. Neutron guides are usually longer than this small piece, so this is only a schematic picture. So they can be 10 meters long, 50 meters long, 100 meters long. So they are very efficient because they allow to transfer the neutron beam up to long distances without big losses. So the losses are usually about 10% or 20% over the whole path. And a next element is the velocity selector. The velocity selector, it is basically a monochromator. So it selects a neutron band of a definite wavelength, and then this definite wavelengths allow us to know from calculation the momentum transfer after the scattering event. So we need to use monochromatic neutrons. It's the same as for the X-rays. In X-rays, usually the characteristic X-ray emission is used, but for the neutrons we do not have characteristic radiation, but we must use some monochromating device. It can be either a crystal or a mechanical velocity selector. Now these red things are very important because they are like saving the life or or closing the beam where we don't need the beam. Then we have some monitor, which is again a detector, so it monitors the intensity of the beam. So in case the reactor power fluctuates, then this monitor is following these fluctuations and will allow to normalize for the incoming flux. Now the collimator. The collimator, in fact, is an empty tube with two apertures, two pinholes in both ends. Here one pinhole of approximately 2 centimeters in diameter, and there is another pinhole here approximately 1 centimeter in diameter. So it provides us a more or less parallel beam of neutrons, and it is not exactly parallel. It has some divergence, but this divergence is necessary because otherwise we would lose much in intensity if we use smaller holes here and here. Now, there is a sample environment is usually more complex, more sophisticated than in this picture. So here we have only a table, and on this table a linear sample changer is installed, and it can be temperature controlled, so it can be thermostated. And then the evacuated tank and the detector inside. I hope clear, no questions to the details. Now this is the this velocity selector. There are two photos of two different types of velocity selectors. Both they contain wheels, many wheels, which are half transparent and half neutron absorbing, and they are arranged so that there is a spiral-like path along them, and if these wheels rotate with a certain speed, then only those neutrons go through which are corresponding to that given speed. And these are the first spectra what we can see today. So actually this is not a scattering spectra, but this is a transmission of the velocity selector operating at different speeds. So these are the speeds of the selector from 3000 per minute to 7000 per minute. And at each speed we select a different band of neutrons. And this upper curve, this black one, this is the neutron spectrum without any selector. It was taken when the selector was taken out. So classically or theoretically, this is more or less a Maxwell-Boltzmann distribution of neutron velocities, but it is strongly biased by different factors. But still, this general shape of or this half symmetric shape of the Maxwell-Boltzmann distribution can be seen on it. Now the sample changer. Here we have a photo of the sample changer, and maybe it's better to show it like this. So basically, it's a moving small car with horizontal movements, and the samples are just put or adjusted in a linear way. Samples can be of various shapes or various types. So, for example, solid samples. So these gray things are a set of wires. So they are a set of tungsten wires which are subjected to temperature treatment of 1150 in Celsius. So they are wires produced for the bulb industry. Then this is a photo of a typical sample holder, a quartz cell, which is used for liquid samples and also for powder samples. And finally, this is the setup of various marble samples or ceramic samples, which are fixed with this screw in a way that we measure the scattering with all three directions of these or orientations of these cubically cut marble samples. Now, what is the main part of the instrument? And the most expensive part of the instrument is the detector. So the common detector types for neutron scattering, so they work in two principles. Either they use the nuclear reaction of helium, of isotope of helium, and they produce energy and thus photons, or they produce a reaction of boron, again with neutron and energy. And finally, they work like a simple gas chamber. So the charge is accumulated on wires. The wires are put horizontally and vertically, and finally we have a grid of the intensities. So this picture is the instrument control software with an image of the detector of an ongoing measurement. Here in the right there is another image of a past measurement, and we see that this is a square matrix, but the active pixels are only around in the circle. So here in the corners there are no active pixels. The color map corresponds to the intensities. So if the color is, at least in this picture, if the color is dark gray, then we have small intensity. Light gray is higher intensity, and blue and red is even higher intensity. Our detector in this instrument has a medium resolution, which means that the detector pixel size is 1 centimeter over 1 centimeter. nowadays, usually higher resolution detectors are built with a typical size or pixel size of 0.5 centimeter over 0.5 centimeter. And for the high resolution special devices, there are millimeter or 2 millimeter effective pixel sizes. So the general scheme of the experiment that, so I forgot to explain why do we have this very long neutron or evacuated guide. So we have this evacuated guide. Let's come to the previous picture. Let's come here. So this two-dimensional detector, so this area detector has the way to move inside this yellow tank. So it can move close to the sample, to this direction, or it can move far to the sample. So it can move between 1.5 meters, being placed here, or it can move far away, it can move to 5 meters. And by this we change the angles at which we can detect the scattered radiation. And this is usually we call these two typical settings a large Q setting and the high Q setting. So the large Q setting is when the detector is close to the sample. This is the sample. And the high Q setting is, the low Q setting is where the detector is far away. And what do we need? We need to measure over an as big Q range as possible. And this makes us, moving of the detector allows to make measurements in both at both or maybe 3 Q ranges if necessary. At each Q range we produce a scattering curve, and in the very end we have to combine these scattering curves in order to get the full scattering curve of the sample. Now let's see what is the a little bit more details. What are the important experimental aspects or the experimental parameters which we need to know? So this is the intensity. The intensity depends, of course, on the intensity of the reactor, that is on the incoming flux. Then this is the angle of view of the detector pixel, which depends on the size of the pixel and the distance between the sample and the detector. Now the detector pixels are not the same. So since there is an electronics and there is a pretty sensitive wire which detects the neutrons, so the efficiencies differ from one pixel to another pixel. That's why we must correct for this non-equality of the scattering efficiency, of the detection efficiency, and we multiply by this factor. Now this is the sample transmission. So if we have, just imagine simply, if we have a very thick sample, then it will absorb all the scattering and nothing will go through. If we have a very thin one, then again this almost everything goes through, but there will be no much scattering. So for a proper calibration, we need to divide it by the we need to take into account the transmission of the sample, and in the very end to divide the scattering data by the sample transmission. Now the irradiated volume, it is the volume roughly 1 centimeter, is the beam size which is falling on the sample. And these last two factors are usually taken together and they give the differential cross-section of the whole sample with a proper normalization. So this number density stands here separately. So this is for the case if we have particles. If we have less particles, then intensity is less, and if we have more particles, then it is higher. So this is a linear factor here. So if we do all the measurements properly and analysis, then we can calculate the number of particles which are in the sample. So we can determine the density of the colloidal particles.
Excuse
now,
me.
yes.
Can I ask a question, please?
Yes, please.
So these cross sections, do you already take them from some table? Somebody has measured them, or you also determine them before you perform your measurement? The sigma over the omega.
Actually, this is a d sigma over the omega. So this is the quantity what we want to determine. So there is nothing tabulated. The tabulated thing is only the atomic cross sections or the atomic scattering cross section.
So
for each element we know it. But this quantity, this d sigma over the omega, this is a characteristic of a given sample.
Okay. Yes, I know. So this is what you actually want to determine from your measurement.
Yes, right.
Okay, thank you.
It's only that this equation is written in this way to be in one row. Otherwise, we must determine this and divide the measured intensity by all these factors here. But this is done by the software, so we will not do that part of analysis. Let's come back. So how we process the data? So we take this two-dimensional picture. So we see that it is more or less isotropic. So first we must be sure that our sample is isotropic, which means that there is no preferred orientation. There can be many kinds of preferred orientations, but let's assume the simplest case. We have a liquid, and liquid is in thermal equilibrium, so normally it doesn't have a preferred orientation. So in this case, the observed scattering is more or less isotropic. It is exactly isotropic. The only difference what we can see if the detector is not perfect. So if the detector has some apparent in homogeneity or isotropic, then we may notice it. But our detector is more or less homogeneous. So for processing this data, we make an averaging around the center of the scattering. So we sum up the data in the pixels along the circles within a given range. We do it many times. We do it approximately 30 times because we have here 30 pixels on one side, and then we obtain a scattering curve which looks like usually it is a decaying function of the angle. So there are a few cases where it is not a decaying function of the angle. So we do this radial averaging separately for the large Q range and for the small Q range. The scattering patterns differ, and in the end we try to merge the data. So we shift or we multiply them by the necessary factors, and finally we get some overlap between the two data. So this overlap here is not too high. Usually it is better to have some 4 points which are falling on the curve. But for simple systems, so this is sufficient. So the sample which gives this scattering picture is a modified silica gel, a xero gel. Please ask questions, because now will come some more difficult parts, some mathematics.
Yeah, I have a question. Sorry,
Okay,
always me. But here, Q is in inverse angstroms, but Q is the momentum transfer.
Yes, it is. Yes, it is.
And it's
this is the usual way we use it in either in inverse angstroms or inverse nanometers.
Why is that so? Because it's momentum transfer.
Yeah, because it's momentum transfer, because it's just easier, because the reciprocal of this quantity will be directly the dimension, what we, the real size space. So basically we work here in the reciprocal space.
Reciprocal, okay, thank you.
So if we the scattering intensity from a sample is a Fourier transform of the real space geometry of the sample.
Okay.
So if we make this Fourier transformation, then we come from the real space, from centimeters, we go to the inverse centimeters or inverse angstroms on this.
Okay. Okay. So time. Okay, in inverse space. Okay, thank you.
So it's just easier to handle. It can be actually given in angles, like they used to do it in X-ray diffraction.
Okay, just I'm asking because now it's different representation than what I'm used to see, so that's why I want to make it clear to myself. So it's a reciprocal space.
Yeah, it is. It is. So this is always in small angle scattering. We use this inverse angstrom or inverse nanometer, and in normal diffraction, in X-ray diffraction especially, people use angle, simple angle in degrees.
Yes.
Or sometimes, if you met it, they can also use the spacing, so they can use the inverse of the degrees. So they represent the data in lattice spacing.
Okay.
So the mathematics is a little bit complicated, but we will not do real mathematics here, but we will see what are the important factors or important quantities in all these scattering expressions. So here again, the differential cross-section. So now this is the characteristic of the sample itself. And this quantity includes the n, this is the number of the particles, not exactly, not straight the number of the particles, but the number density of the particles. Then the volume of the particle itself, some contrast factor. Contrast factor is the difference between the scattering length density of the matrix and the particle itself. And two more interesting factors, which in fact we want to determine from an experiment. One of them is called the form factor, or shape factor, in other words. And this will tell, this corresponds to the shape or to the form of these particles. So these are rather ugly particles. In fact, we don't know the scattering from this particle. Usually we deal with particles which are more regular in shape. They can be spheres, they can be ellipsoids or rods or flexible cylinders. But for such random shaped particles, there is no mathematical expression for this parameter. So the good thing in this equation that the form factor, so this part can be described by some formula, and also this part, the structure factor, can be described by some formula. So for the next 2 minutes, we forget about the structure factor, and we just think that we assume that it is unity, so it is equal to 1. So the scattering cross-section is proportional to the number density, to the contrast in the square, and to the form factor. So the form factor, how it looks like. Let's take a sphere. Sphere has only one parameter, this is the radius. A radius of the sphere can be 5 nanometer, it can be 7 nanometer, and the form factor is analytically calculated, and it can be expressed as this expression. So sine QR minus QR cosine QR, and divided by QR in the third power. So what we see that the parameter in this equation is the radius, and the other quantity is the Q. So the Q is here, the radius is here. So in fact, what we see, we want to see the intensity in the function of the Q. And from this shape of the curve, we can determine the radius. So here in the plot, this formula is depicted for two different sizes of particles. And what we can observe that if the particle is smaller, so it's 50 angstrom in diameter, then the scattering pattern has oscillations. It will always have oscillations because of these trigonometric functions. So it has oscillations, but the oscillations tend to be at higher Q. And this relation is very general. So this is a demonstration of the relation of reciprocity or reciprocality of the real space and of the inverse space. So that means if the size of the particle is large in the real space, then the scattering pattern goes to the small q, small angles. So then it shrinks towards 0. And it also means that if the size of the particle is too large, for example, it is 700 angstrom or 7000 angstrom, then this curve will be very much moved or shrinked towards 0. And there is always a cutoff, there is a limit. There is a limit below which we cannot measure. So if this particle will be too big, say 1 micron, 1 micrometer, then we will not see nothing. So only this tail is decaying very, very strongly towards with the increasing of the Q. So this gives us approximately the picture why we have a certain range over which we can measure different particles. If we do the opposite, so if we have a 5 angstrom particles, so this is very good for the experiment. But if the particle is only a half angstrom, then this curve will be something like this. So it will be nearly flat over this Q range, what we can measure. So again, it will be not detectable. Of course, there is it will be not possible even to construct such particle, because below 1 angstrom we cannot make anything solid. So it will be already the interatomic distances. So this was the form factor of a spherical particle. Coming back here, this is the place where the form factor is. And this is the differential cross-section is basically the scattering intensity, what we see. So what we measure is the scattering intensity, so this quantity here. A bit more complicated particle, but again, an ideal particle is an ellipsoid of rotation. We plot here only ellipsoid in which one axis is longer, the other one is shorter, and the third one is the same as the shorter one. So it is an oblate ellipsoid of rotation. So if we make the model, so the formula is a bit more complicated, so we don't show it here. So we make a model calculation, then we see that the ellipsoid still has these oscillations, but as we make the ellipsoid longer and longer, so these oscillations, so they tend to smear. So it means that they tend to be not very precisely determined. So it means that we have not a unique size in this object, but we have a whole range of sizes. We have a radius like this, we have a radius a little bigger and a little bigger and even more big until we reach the maximum radius. And for this reason, the the positions of the maxima and minima are also modulated, and finally they lead to the smearing of the oscillation. Now this part of the curve, it comes, so this comes from another chapter. So there is a theory, or there is a theoretical model of an elongated particle, which is a cylinder, which is a cylinder which is very long in one direction and very short or very thin in other two directions. And the scattering pattern from a cylinder will have a asymptote, or we have a part of the scattering curve which is linear in this double logarithmic representation. And in particular, it will have the decay, it will go intensity proportional to Q on the -1st power. So this, if we see a part of the scattering curve which is nearly straight in logarithmic plot, and the slope is -1, then we will know that we have some large or some long objects in this sample. So such large objects can be needles or nanoneedles, or they can be long micelles, cylindrical micelles, or wires. So for example, carbon nanotubes. So they are pretty good model for this. So this was the ellipsoid, and finally a third shape which can be calculated mathematically is the real cylinder. So the cylinder has two parameters. It has a height and it has a radius. And here, this is a straight part is much more pronounced. So, and if this cylinder would be much longer than in these pictures, then this straight part would be much longer again. So here we see the difference between the two dimensions of the cylinder is a factor of 10. So if this would be a factor of 100, like for carbon nanotubes, for instance, then we would see only a straight line which is decaying with a Q in the -1st power. So these were the three simple shapes. Now there are, besides the shapes, there are a few approximations which are useful. So suppose we don't know the shape of the object at all. Then we have the approximation which is valid for the smallest Q. It is called Guinea approximation. So it means that from the slope of this at this part we can determine approximately the size of the object in an average term, and this average parameter would be called the radius of gyration. So this can be determined, and this will be, we will use it in the next parts. And the other approximation is the Polar approximation. It means if we have a particle and it has a flat or nearly or smooth shape, a smooth surface, then with a good approximation, the scattering intensity will decay with this power or Q in the power of 4. And this is usually valid for the high Q range only. And in case this power will be not 4, but say 3.5 or 3.7 or 4.2, then we can conclude something about the characteristics of the surface. So this surface can be rough, or it can be smooth, or it can be fractal-like. And in many cases, these things appear in the real experiments. Now, so these were the few models for the form factor, and now there will be only a single sentence about the structure factor. So the structure factor can be, as I said, it can be absent. If it is absent, it means that it is its value is 1, so it would not affect the scattering intensity. And this happens if the particles are very far from each other. Maybe I didn't mention that a structure factor means that it gives information about the distances between the particles and about the way how they are arranged in the sample. So if they are arranged like in a crystalline way or a half crystalline way, or if they are random, totally random, or if they repel each other, or if they try to stick each other, all these cases will lead to different forms of the structure factor. With more mathematics, so the structure factor is the Fourier transformation of the GeoPhar, and the GeoPhar is the distribution of the distances between the particles. So the probability distribution of the particles at different distances. And the characteristics of this function is that at very big distances, usually the particles don't feel each other. That's why there is no this term goes away, and this means that also the SQ term has a form in which in the small q it can be either bigger than 1 or smaller than 1, and at large q it will always be equal to 1. So it will be equal to 1 when there is no correlation between the particles, for example in very dilute systems. And also it will be 1 if the q is very big. So they are, again, since the reciprocity, I will look in the dictionary how to spell this word. So because of the reciprocness of the inverse and locals and the real space, for very large distances, the SQ will be 1. I'm sure you don't understand everything. Please ask questions. Just for these 2 slides.
So what is the criterion for saying whether it's dense or not? What electrostatic long-range interactions do you take into account?
Right. This criterion depends on the interaction. So I mean the criterion of denseness. So if the interaction is very small, so for example, if the particles are not charged, if particles are not charged, it doesn't mean that they don't interact. So particles always interact.
Yes.
Just because they cannot approach each other closer than their dimensions. So this effect is called the excluded volume effect. So if we have a system in which there is no electrostatic interaction, then we have still this excluded volume effect. And for this case, the diluteness starts to be true somewhere about 1 or half %, a volumic percent or volumic fraction of the particle in the system.
Okay, so the measure is the volume of the particle. Then you compare the distance between particles to their volume.
This is for practical way it is useful, because this is the way how we prepare usually samples. So when we mix the colloidal particles with the solvent, then we know how much gram or volume to weight. And we try to prepare samples which are approximately 1% in mass fraction or in volume fraction.
I see.
So very often the volume and mass fraction are not far from each other.
Okay.
And the other case, if we have charged particles, then depending on the charge, they repel each other stronger and stronger. And in this case, very often we even cannot reach such dilute system which would not interact. So this is usually happening for micelles, because micelles are made of surfactants, and surfactants are basically ions, and the half or a part of these ions are always dissociated in the solution. So all the micelles have some charge, and they always repel each other.
Yes, but also in the cell, like if you are looking at the membrane, you also have lots of ions and you have charged parts and yeah, okay. So this is a complicated problem, I would say.
Well, but I would say that there are very good ways to handle this problem. So there are many decades of experience. So my statement is that they can be handled very well.
They can be handled, okay.
So the simplest thing is to make a dilution series. So you prepare different concentrations and then you see the difference between them. And if you are accurate enough, then you can extrapolate to the zero concentration. So if you can make such accurate experiments, then you can extrapolate the scattering curve to the zero concentration.
But this is only, you're talking about the concentration like for liquid samples. But if you have a solid sample, then it's not so easy.
Yeah, for solid samples, it's actually not possible, but usually solid samples, they are not of this type. So they are not of the form factor, structure factor type.
Okay. Okay. Yeah. Well, mine are, but never mind. Okay. Thank you.
Well, so this was more or less the first part of our lesson. Let's see what is the time right now. I would ask you now to watch this video. I don't know if you have already seen it. And I'm not sure how you can copy this thing. And then we come to the next part. So let me copy this.
Okay. After the video, there are other two questions in the chat. I think now you can read. Otherwise, I can read it for you.
I will come. Okay, now I read it. Just a second.
Okay.
Compounds of isotopic elements. No. So the question is if compounds of isotopic elements to be used as neutron sources. So they are radioactive elements like uranium, for example, or americium. So they can be used by neutron sources, but they are not useful for scattering because those neutrons have a very high energy and very high speed, so they cannot be used for this kind of our exercises.
Thank you very much for your very kind response.
I don't know if this was what you meant.
Yes, because I have listened from colleagues that they make neutronography by sodium chloride source, where the sodium is the heavy isotopic element. And they use photomultiplier as a recipient, but their device is much more simple than the equipment that you are using. So
yes, then this is because probably they use it not for scattering, but they use it for transmission or radiography, for example.
Yes, maybe for transmission, yes.
Because in this case of radiography, you can use actually whatever you can detect, X-rays or neutrons, with high energy neutrons. And there are many industrial devices which are based on the same principle. So you have a small neutron source. You can insert it, for example, in a pipe, in a gas, undersea oil pipe or gas pipe, and then see what happens on the other side of the source. So to measure the transmission of the through the wall of the gas pipe, which means that you can test the quality of the metal if it's not corroded or it's not damaged. So this is basically radiography. So it's not really neutron scattering.
Yes, thank you very much. The device that I have seen is much more simple than your equipment. It was as a children's toy. It was sodium chloride source. After this, you put a tablet of the sample of the specimen, and on top of this two things, the source and the sample, there was just a photo multiplier. It is multiple photo sensor, and they obtained information from some kind of secondary photons, which were obtained from the collisions between the irradiated neutrons and the particles of the sample. So since they have explained to me.
Well, it's interesting. I really don't know what kind of information they can obtain by this way.
Yes, they also had some difficulties because they explained to me that of the data they obtain need some very complicated statistical information. So, and the radiation should be for several days or something like this. They collect the information and they submit to some statistical data treatment.
Yeah, this is actually correct for all these tabletop sources, that they are very low intensity compared to these large scale facilities. But still, they are, of course, they are cheaper and they are more available, so they should be used whenever it's possible.
And I have a question now. Do you use some kind of statistical data treatments? Because maybe some statistics should be obtained before to make some data interpretation.
Yes, many, but everything is reduced to data fitting, in fact. So we need to accumulate more or less good statistics on the sample, which is visually appealing, which means that if we have a more or less smooth scattering curve, then we can make a data fitting by models. And then if the fit goes through the data points, then it means that this satisfies both the statistics and both the model.
So we can obtain some reliable data by repeatability and data reproducibility.
Yes, but the same, if you measure the same sample twice within 1 hour, you get essentially the same.
Yes, it depends on the sample as well.
Yeah, surely. So there are, for example, the time-depending processes. For them, it is more tricky, so we cannot always follow them with a good enough time resolution. Sometimes every 2 seconds, sometimes only every 20 minutes, depending how intense is the scattering.
So you can make also monitoring of chemical reactions, if I understand, if you can apply data for each 2 seconds or whatever, you can observe some reaction system.
Well, yes, well, it's not always chemical, but at least there is some process, for example, mixing or unmixing, so this can be followed.
Yes, thank you very much for your very kind attention.
Welcome. And there are 2 questions by Vladislav. If it's possible to obtain structural information on pattern solid thin films, well, depends. Pattern metallic layer. Yeah, in principle, yes, if this pattern is dense enough in the sense that the repeat distance between the I don't know, holes or whatever is there is in the range of small angle scattering. What kind exactly? So there are nanoporous alumina or any kind of films which can be made very thin. Or even the silicon oxide substrate or pure silicon substrate can be made patterned with holes, and then it will give diffraction. It's periodic nanodots. So usually this works well for cylinders. So if we have at least long cylinders parallel, but nanodots, just nanodots, they give much weaker scattering. So I'm not sure, but it should be tested. Probably the easiest thing is to test it by X-rays, if it works. Another thing, if you can show me an image, a microscopy image of these things, then I probably can make some guess whether it's feasible or not. Okay, welcome. So we can watch now a short movie, but maybe we can take also a short break. I don't know how you feel about that. I suggest that we take now a break, a pause for coffee or air, 5 to 10 minutes, and then come back again here. So hi again. So probably this is over. If you have questions which were not clear at the video, then please ask. And if not, then I will answer the question about the electromagnet by Vladislav. So the electromagnet can be used for two things. So first, it can modify the sample. So it can, for example, align something which is on the sample, like magnetic particles or liquid crystals. So it can orient liquid crystals. And the second way to use the electromagnet is to align the magnetic moment in a solid sample, in a steel sample. And this is useful if we want to see the precipitates in an iron, for example. If the iron is magnetic, the iron phase is magnetic and the precipitate phase is non-magnetic. For example, this is the or popular ODS type of steels, which means oxide dispersed steels. So there is a small amount of oxide phase and it is non-magnetic. And if we eliminate the magnetic scattering by using electromagnet, then we can see purely all these small precipitates. So this was about the simplest possibilities of using the magnet. In more interesting fields, the magnet can align, for example, the flux lattices in such type of materials, or it can align also the biological samples. For example, it can align the membranes in a way that they stay parallel to the field, and by this way the intensity is very much increased because they add up coherently. So the orientation, the pattern will not be any more isotropic, but it will be oriented, and this improves very much the statistics. So now we can do two things. We have, in fact, 1 hour left, so we can watch some videos how about the sample preparation and experiments and beamlines, or we can make some data analysis, or we can do both. So let's start at least with a few of these short videos which I made just to show our instrument from a close distance. do you see?
Yes.
Okay, so this was let's start from the very beginning. So we enter the guide hall. It's an awful noise. This is the overview of the experimental hall. There are various sorts of finished or half-finished steel installations here. The interesting is this orange channel, which is the shielding of one neutron guide, which leads to another experimental station. And the second one is this yellow tank, which is the yellow submarine spectrometer. And we must climb on these stairs over the shielding. This is the view of the neutron hall. It's very crowded, so there is no much space, and there are lots of various items. These cubicles are the instrument control rooms, just in front of us and in the neighborhood or in the next one. Okay, so this was this one. I'll show another one. Unfortunately, the other one was filmed in a different way, and I didn't manage to rotate the movie. So here we are on the other side of the beamline of the 3 neutron guides, and the big one is the yellow submarine, the normal SANS instrument, and this small one is another. It's called focusing small angle scattering instrument. And the control room is contains 2 computers and some electronics and some chairs. So there is not much more interesting here. Now we come closer to the position where the sample is located. So these various panels are various shields against thermal neutron noise, which is everywhere in the guide hall. And the orange-yellow concrete blocks, they are biological shielding, which means that they absorb gamma radiation. Okay. Now this is again the control room. It's the electronics. These are connected to 2 computers. One computer controls the external devices. It connects to the electromagnet and to the thermostat and the motors, various motors, and the other computer makes the actual experiment running. So this is the instrument control software is running on that computer. Probably, and this kind of setup is very common to all neutron instruments. So this is the panel where we can close and open the shutter when we want to enter the so-called irradiated area. Stop it. what we do when we start the experiment, then we first come and close the beam. So this is absolutely obligatory. So that's why it's emphasized also in this video. So this should not be forgotten, and also the beam opening should not be forgotten, which is a common mistake when making experiments. Now, for accessing the area with the samples, we must again overcome this huge barrier with many steps and very ugly shielding materials, but then it works. So this is the sample table. So the sample table is motorized. It can move vertically and it can move horizontally. So this rail can move with this sample holder. There are various sample holders. Some of them are connected to a temperature control device, and this one is not connected. So we see that it is purely just a piece of aluminum. Now we are loading samples which are in quartz cells. I have shown you before what we see, and inside there is some colored powder. So this is an inorganic cerogel doped with some metal, probably iron oxide. So these are the quartz cells. So they are made of quartz glass, and they are usually 1 centimeter in width. And that's why we need to use such a focusing or such a beam collimation which fits this size. So the 8 or 7 millimeters is the usual beam size for these cells. Now let's fasten it a bit. So it's the same procedure again and again. So we must load all the positions, or at least several of them, because after that the experiment is done in an automatic mode. So it's this screwdriver which just fix the holders in the rail. Okay, let's stop it and come to the next one. So when we loaded the samples, we need to select the most appropriate pinhole for the measurement. So since there are different kinds of sample cells, so there is this large one, what I just took off, it was a 12 millimeter pinhole, and this is an 8 millimeter in diameter pinhole. So this would match the size of the quartz cell. 7 millimeter would match even better. So all these operations here in this area must be done when the beam is closed, when the shutter is closed. A special sample which is measured regularly together with other samples is needed for the calibration. So this is a cadmium sample. Cadmium is a metal which has a very huge cross-section for neutrons. So it absorbs the neutron beams. So when it is placed into the sample position, then everything what is registered on the detector is the noise which is coming from somewhere else, but not the sample. And when making the data processing, we subtract this background noise or background scattering curve from the real scattering curve. So this is a simple cadmium plate. So the most important is to open the beam. Sometimes we can forget it after the sample manipulation and then launch the measurement very quickly and then leave very quickly and don't check whether it is working. So this is about it. just a part of the collimator tube. So this is a simple aluminium tube, 5 meters long, with a vacuum inside and some aluminium windows or sapphire windows for the neutrons. So this is how the experiment is being performed. The next part of the experiment is the setting up the program in the instrument control software. That is to write the parameters of measurements, how much type, what is the sample name, what is the order of the measurements, what temperature, and what detector distance and what wavelengths. So after all these parameters are set, then we start the measurements, and usually it lasts for about 12 hours in an automatic mode, or 20 hours. So usually, at least at our source, we don't sleep here with the experiments. So there are other facilities in which the neutron intensity is much higher. Then they need to change samples every few minutes for making full use of the neutrons. And then the experimental team is usually spending the whole night with the instrument. What is next? So next, we shall make some data treatment. But please, if you have questions now, then let's talk about. I'm stopping the screen share. So let's ask questions. Normally, when this course is given not online but with presence, then the students go and they make their own measurements. So there are a few samples. Either they can bring samples which are made by themselves, or they are interested, or make test measurements, or we use a few samples of ourselves, and the students are doing the whole cycle of experiment, which is at least what is possible within a few hours, or within 1 or 2 days during the hands-on training course.
I have a question.
Yes.
What is the annual expenditure for maintenance of all this equipment, and how much people is in charge with the maintenance of the equipment? Because I see that it is rather big and rather huge equipment, very impressive, really.
Yes, well, it depends always on how much stuff do we have. Sometimes it's more, sometimes it is less. At the moment, we have 4 scientists who are working on this beamline. 2 of us are permanent, or we are, say, in charge of the instrument. And there are 2 postdocs who are using it in a regular basis and also use it in or help to the users, external users, if they come. So there are these 4 scientists, and there are a technical group, a small technical group, who sporadically they come and solve problems if something get broken, or they do also the development of the various mechanical or electronic parts of the instrument. So this is the general. But also this technical group, they maintain, or they take care about all the 5 or 6 instruments which belong to us.
And what are these devices unique for Europe?
Not that unique. So we are proud to say usually that they are unique for Central Europe or for East Europe. So this is the only place where we have such a good instrumentation. Otherwise, in Europe, there is a much bigger centrum in Grenoble, which is called ILL, and a similarly big center in Munich, near Munich, in Garching. which is called Forschungszentrum Jülich. And they have, each of them have approximately 3 small angle scattering instruments, 3 or 4 beamlines, and correspondingly many more instruments of the other types. Whereas we have a 1.5 small angle scattering instrument, meaning that one is this one, the pinhole one, and there is a smaller one, which is a focusing one. And another difference is the intensity. So the neutron beams from the Munich reactor and from the Grenoble reactor is about 10 or 20 times higher, the flux. Which means that for certain cases, so they are necessary, but for most of the other experiments, our beam intensity and our parameters are quite sufficient. So this is the picture in Europe.
Yes, thank you very much for your very kind attention.
Now I'm reading the question, the annual financial expenditure. Well, this we don't know, we really don't know. We can calculate, but we never do it. Because it's very sporadic. So if something gets broken and it is expensive, then it needs to look for some extra budget for that. Otherwise, about finances, so the most expensive thing is, of course, the neutrons themselves. And this is fully done by the Energy Research Center, which means that they run a reactor, and they provide us with the neutrons. And the cost of this reactor running is much higher, of course, than the cost of all the individual instruments. Well, so we can do some analysis. Have you used any kind of software for analysis? I don't know if you have downloaded it, but there was an announcement that for this practical session we will use 2 kinds of software. And if you download it and install them, then it's fine, and we can do together these exercises. Tell me please if you have them. Well, okay, so probably you downloaded almost all, and probably you have never used them because you didn't need it. So we can do 2 things. There is a general software which is called GNU-plot. The question if any one of you have used it ever. So this is the general data plotting software.
We never.
Never. Okay, then there are 2 ways to do the exercise. Either we use the GNU-plot, which will be useful for you because you will learn something new, and you can use it for any kind of presentations, or we shall use a specialized software for analyzing the small angle scattering data. Which one do you prefer? First, let me share you some data files so you can download the files for this training from this website. So this is the repository of our institute, and there you can find some text files which are actually measure scattering data. Now the software, the software is called Sas View. So if you Google these things, then you can download this software. And the other one, which is useful, this is the GNU plot info. So tell me, please, if you are ready to launch this GNU plot software. Have you installed it? Okay, so we shall do it slowly. So for those who don't have it for any reason, then I shall do it on my screen. So first, let's see these data files. So please download from this link all the data files. So their list or their names are like Ag behanate. So this is silver behanate. Then there is apoferritin. There is PMMA sphere. Are you done with that?
I don't know what about the others, but I can't reach the page you sent.
Really?
Yeah, but probably it's my connection.
Oh, which page you cannot reach?
The one for the data.
For the data. But what does it
Yeah.
say?
Can't reach this page.
Right, but
So probably
what does it say? Just cannot reach?
yeah, but probably it's because I am at the laboratory and so it doesn't. I don't know what about the others. If they can do it, then it's my problem.
Okay, please give feedback, everybody, if you could download the data. Could you please tell me who could not download the data?
Me, I'm Federico.
So you opened the link and you didn't download the data files. It's strange. Normally they can be downloaded. But since they are text files, maybe you need to save them by some right click or left click or something.
Okay, I will keep trying. Thanks.
Hmm?
I will keep trying.
I uploaded there a zip file. Probably you can download the zip file now. All right, so this, I'm sorry, this took some time. So let's start the software. Let's start the software Sas View, because we have not that much time. Sas View, have you downloaded the Sas View?
Yes.
So we click, it displays a lot of panels. I shall make now a screen sharing. So this is how the Sas View starts. Now in the upper this menu bar we have the file and we have load data files. So let's load the data file. Now we need to find our actual folder. Have you managed to reach this step? Well, if many of you can do it, then I shall do everything on my computer. Please tell me what is the what you feel better. Nobody is reacting, so this is not very convenient.
Oh,
Please
we
tell
are
me if somebody can do it with this Sas View fitting.
I'm following on your computer because I couldn't download data, but others are writing in the chat and I think you can see it.
Ah, the chat, oh yes.
Yeah, most of them are saying that let's see from your PC. So
Oh, okay, so this is a more lazy version, but still it's good because we can probably understand everything even like that. So the first thing will be very familiar. So I shall open this file which is called AG Behenate. So it means silver behenate. Sorry, I'm not in the right screen. Yes. So this silver behenate, it is a text file. So it contains 3 columns of data. And we can plot it immediately. So we shall use this button here, send to fitting. So we can make a send to plot, but instead we make it send to fitting. AG behenate, the file. But now it is renamed from txt to extension ede. It doesn't matter. Yeah, like that. Please refresh your browser with these data files. so that they appear. All right. So I'm sending the data to fitting, and this is how it looks like. So what we see very, very noisy, very ugly data, in fact. So this is one of the test measurements what has been done sometime. What we see that, what should we know about the sample? The sample is a powder, and it is crystalline. It contains crystalline peaks. So these peaks are in fact a real normal diffraction peak. This is the second order, this is the first order, this is the second order. But the layer distance between the atomic planes is so big so that it falls into the range of small angle scattering. And we use this powder for calibration because we know exactly the spacing. So now we make a fitting. So the fitting panel is somewhere usually below this graph, and it is here. And first we have several categories, and then several models, and then we can have several combinations of these models. So from the categories we select the shape independent, because this is now only a crystalline peak. And now we have a Gaussian peak, for example, a Gaussian peak. You see? Is it fast enough that you see what my cursor does in the screen?
Yeah, it sounds okay.
Okay. So this is the difference graph. I make it minimizing. So first, these are the parameters. So this is a single peak, a Gaussian peak. It is a scaling factor, a background, a peak position, and a peak width. So the peak position first we set by hand. So it is about 1. So this is 0.1 here. So the peak is around 1. This is in nanometer now. So we just write here 1. And then we make a compute. And what we have? Do we have something? No, we don't have anything. This was too small. Now we have something. So now we put the background. The background is around 0.01, 0.05. So the background should be 0.05. So we just put it like that. Compute. Now the background is approximately all right. The peak position is shifted, you see, because it is not exactly, but this is the task of fitting to, and also the scaling is not so good. So we shall set as free parameter the scale factor and the peak position. And here we make the fitting. Now it moves, and it nearly precisely fits the data. And we need also to set free the sigma. So this is the width of the peak, and also the background can be changed now. Okay, so what we see that the first point here, it goes down. So this is nothing wrong with this. It is bad data, and this bad data is because it was very close to the beam stop. So in fact, this point should be neglected. The same as with the last 2 points. Here, this simple model did not contain only one peak, but we can develop this model so that it would contain 2 peaks, and then it would fit them simultaneously. So this we don't need to deal with this. This was just the demonstration for the very simple fit by using this software. Now let's see some more complicated thing. Tell me please if some of you could do this on your computer.
They say yes. I don't know if you see the chat, but say yes.
Yeah, yeah. Now I'm looking the chat. There are at least a few positive responses, which is encouraging. But anyhow, so this is the the thing to do it is not complicated. So the software is complicated. So the software was written by a huge team of developers in over the last 5 years. But in fact, the same can be done by much simpler softwares, which are commercial or freeware or anywhere. So let's now select another data, load the data. Again, we go from the menu bar in the top, we make load data, and what we do, if we take the simplest model is a sphere. Let me stop sharing the screen for a moment. How to do it? Stop share. Do you see the screen? Hello.
Yes.
I tried to share the whole computer. Do you follow it? Is it okay? Okay, so this is what we will do. So now you see my PowerPoint presentation. Do you see it?
Yes.
Yes.
All right. So now I'm sharing the whole computer, and I will switch between the windows. So the simplest thing for small angle scattering theory is the sphere, and we shall now take these very nice polymer spheres. So these are commercially prepared nanospheres, and they have been measured at some instruments. So this is the same fitting what you get soon using this software, and this is an electron microscopy picture of them. So these are colloidal polymetacrylate particles. So now we go to the software, we select the PMMA sphere, open, and in this Data Explorer panel, we turn off the silver behanate, and we keep only the PMMA sphere active, and then send it to fitting. So we have sent it to fitting. This is how the data look like. So again, what you can see that the first point has this very huge error bar. So this is because the data point is very close to the beam stop, and around the beam stop there are not many pixels which are really active. And in this case, it probably happened that only one of the pixels was active and the others were masked out. But still the data look good. It's only that very big error bar will make this point more or less useless. At least the fit will not be sensitive to this point. And the same can be observed in the very end of the Q range. So here, first the intensity is low, that's why the error bars are big. And the second, that they are on the edge of the detector, and very often they just fall out of the edge of the detector if the beam is not well centered in the middle of the detector. But still these data are useful or usable. So if you look close to this picture, you can see that how these data points are spaced here. And you can recognize that this is probably constructed from two ranges. So one of the low Q range was measured here, and the high Q range was measured here. So this data consists of two, if not more, separate measurements. and they are merged together. Now we find our window which can be used for fitting. And now we were in fit page 1. It was for the peak, and fit page 2 is for our new data. And now from the category we shall select the appropriate category, which is the sphere. Now there is sphere, there is here nothing yet, but there is a tons of options of various different spheres. So you can see that the model is simple, but the sphere can be a core shell sphere, a binary hair sphere, a core with multi-shells, and a fuzzy sphere. Fuzzy sphere means if the interface between the sphere and the surrounding is not smooth or not sharp. It can a couple of spheres like purse or onion and so on. So we use the simplest one, the sphere. We close this graph because we don't deal with this one. So what do we observe in this picture? So we observe this model curve with default parameters which are here. Scale 1, background something, radius something, radius 50. So what we see that these oscillations, so they resemble somehow the data, but they are wrongly placed. So this means that the size which is included in this model is 50 nanometer. It is not corresponding to the data. So what happens if we modify this? We put, for example, 70 and make a computation. So we see that this oscillating pattern shifts even more to the left. So clearly we have a much higher size here in the model than the size of the real particles. So we go back to 50. The pattern moves back and we can do it. In fact, we can fit everything by hand. So we don't need this software so it's not that much necessary. So by some minutes of varying this parameter, we can obtain a very, very, very accurate fit. But let's make the software doing it. So what would happen if I would relax this parameter? So it will start fitting, and I will relax also the background. You see the background is much lower than the real experimental background. So the experimental background is somewhere on this level of 10 in the power of -1, so 0.1. So if I by hand I put here 0.1 and don't change the other parameters, then I can make a computation, and now at least the end of the curve matches more or less the data. So we can stay with this background and we can vary only this single radius and see what happens if the computer is able to fit the curve. Fit. So now I'm pressing fit. Well, I'm pressing it once again. It went from 50 to 33, and 33 in fact is much closer to the positions of oscillations. Not very accurate though. But this is normal. So if we relax only one parameter, then we cannot achieve a good fit. So let's make the background free, and also let's make the scaling free. Now, what are these two parameters here? So these are the scattering length density of the sphere, and this is the scattering length density of the solvent. So if we remember from the equations, So these two parameters give the contrast. So this is the parameter key, the contrast. And if you see the contrast is, where is the contrast? The contrast is the difference between the density 1 minus density 2, and everything is in the square. So if we try to vary these parameters, for example, diminish the contrast, saying putting here 3, then the difference between them will be smaller. Then what will happen with the curve? The curve will go down. However, if we change these parameters, then we are not able, or we are not allowed to change the scaling factor, because this goes in the same direction. So we can either fix the scaling to 1 and vary these parameters, or fix these parameters and vary the scaling. So let's vary the scaling. So this scale parameter is relaxed, means it is to be fitted, the ground to be fitted, and also the radius to be fitted. And now we make the fit. Fit is fast. Now the fit follows the oscillations pretty well. You see the second one is matching the oscillation of the data. The third one is also, and the rest is not resolved here. Now, what are the reasons for this discrepancy? Any idea, people, please? So here you see we use this model sphere, and for the structure factor we did not use any structure factor. Because we assumed that this system was dilute enough, and indeed this system was dilute. It was 0.5%. So even at 0.5%, some structure factor would appear, but we don't care about it now.
But if this is small, you said that these amplitudes are not are small in certain cases.
Are what small?
The amplitude, the peaks here, they're small. They are not so pronounced like in the fitting model.
Sorry, repeat please. I didn't hear it well.
So when you compare the fitting, the fitted curve, you have nicely defined peaks.
Yes.
But if you look at the data, it's it's just smaller. So they don't fit for the size, the shape of the particles. So spheres are not a good model.
Yeah, exactly. Did you see the image in the presentation?
Yes.
To me, they look like spheres. I mean this. Okay, we did not measure this sample exactly, but our spheres were not very far from these spheres.
Well, in the real world, it is impossible to have ideal sphere. It is also truth.
Well, this is true.
But maybe they are overlapping. I mean, they are maybe screening each other in some way. If you said it was diluted, but what if they are making clusters?
Yeah, exactly. So this is one possibility, that these spheres, they stick to each other, at least few of them, and make clusters. Then they will surely distort the scattering picture. But the fact is, if there is a cluster, then it can be regarded as a bigger object. And the bigger object will have a scattering which comes somewhere here. So the scattering intensity will be bigger at the small angles. So it means that the main factor of the discrepancy is not the clustering. But rather the previous remark of one of the boy students who said that nothing is perfect in the nature. Yes? Or what was your exact sentence? So you said that it's not possible to make perfect spheres.
Yes, the ideal things never exist in the real world. They are just
right.
a human fiction. So
Okay,
it is
but
never ideal
this is
sphere.
Right. This is the
cylinder,
philosophical aspect of the problem, but the practical aspect is that the spheres are indeed not exactly the same and not exactly spherical. Just because chemistry doesn't allow you to prepare such perfect spheres. So it means that the spheres are not the same, but still we can say something that they are nearly similar. So for this fact, we introduce the notion of polydispersity. You know polydispersity, what it means. So it means that the spheres, they are not exactly of the same size, but some of them are a little bit bigger, some of them are a little bit smaller. So in fact, there is a distribution, a size distribution of the spheres. And this size distribution can be very sharp, so they can be very close to each other, or it can be very not sharp. And if the sizes are different, then the scattering comes from all of the spheres. So it means that there will be bigger, smaller, and we must sum up all the scattering curves. And it leads to a very simple phenomenon, which is called smearing or smoothing. So it means that all these very sharp oscillating patterns will overlap. If we, for example, so if we put here, for example, 40 here, 40, and compute, then you will see that the picture moves a little bit. So it went a little bit to the left. So imagine that there are 40, there are some which are 35, and they move a little bit right. So the minima will be not in the same places, the maxima not in the same places, so everything will be added up, and finally it leads to a smearing like that. So this is one of the reasons, but there is a more important reason, that the resolution of the measurement is not perfect, and probably this is a more important message for the small angle scattering business, that it is generally said that the small angle scattering is not a high resolution or not high resolution technique. So which means that we cannot do it because if you remember the pinhole and the sample, what I showed in the movie, so even the pinhole has a size of 1 centimeter. This means that neutrons coming from different directions, in fact, they all scatter and they all contribute to the scattering. So this leads to a smearing of the resolution. So it means that the resolution is not so good. It's not absolutely good. And for this, there is a way to take it into account. And this is here, if you follow my cursor, in the fitting panel, the set instrumental smearing, we can select a custom pinhole smear option. Also, we can select a custom slit smear, but this is for another type of measurement. For the custom pinhole smear, so it is given in percents. So if we select here, for example, 5%, so let's assume that our resolution is 5%. Now let's see what happens. We press compute. You see that the pattern will be less, so the peaks are not so intense now. Now if we change it to 10%, because in fact the resolution of this experiment was around 10%. But this is only an average resolution. Now we make compute again, And now we see that it is now much more close to the data. We just need to make the fitting again to get back the proper radius. Okay, now we obtain this kind of agreement between the experimental data and the model. So it is still not perfect, and there are two reasons again for this. The first one, that this resolution correction, what I introduce here, it's 10%. It is not exactly 10%, but it is different for the different points of Q. So in fact, every point in the detector at every angle has a different resolution, and it varies from 10 to 15% because it depends on the position of the pixel in the detector. But this software takes into account in an average manner, and this 10 or 12% is more or less satisfactory. So here with 12% of experimental resolution, I could fit it visually perfectly, at least. Well, not perfectly, but good enough. Now, why it is going down here, it's another problem. So it is clearly below the data points. And this is because the background subtraction is not, it cannot be done perfectly. So probably here the background is not subtracted enough. As for the particle agglomeration or structure factor, so you see that the line follows the data in the very small q, so it does not deviate above or below. So it means that practically there is no interaction or no big interaction between the particles. Now let me show another effect. So we can introduce this interaction into the model. So now we shall consider a hard sphere. Hard sphere. Hard sphere means that they are solid things, and the volume fraction here. The volume fraction is 0.01 roughly. And what happens if the volume fraction is 0.01? Now it needs to be fitted again because the other parameters. Because by volume fraction we also divided the content of the spheres by 100 times. So we need to make again the rescaling or the fitting. So let's make a fit. Okay, so what we see that with this volume fraction already some deviation compared to the previous case is seen. If we put this 5%, then we see that the curve is markedly below. And here note that I did not fit the volume fraction, but I imposed. So that then you can imagine that if you have a volume fraction of 5% for this case of hard spheres, then the scattering data should be lower here. And if you have a even higher, like 15%, so a really dense system, then this is how it will look like. If we have here 30, which is a really high. So you see that the rest of the scattering curve is fitted pretty well, but the deviation is only seen in the smallest q, in the range where the structure factor, where this structure factor is operating.
The volume fraction is the part of the volume which is occupied by the particles, if I understand.
Yes, it is. Yes, it is. And in this case of spheres, it is nearly similar to the mass fraction. So you load 1 gram of spheres and 100 gram of water, then you are at the 1% volume fraction. Now, if we make this as a free parameter, then it should return after some efforts, it should return back to this. You see, the fitted volume fraction is very, very low. So it is not. It is smaller than the error bar of on the same parameter. So it is not relevant. So he cannot fit the volume fraction. So this system is so much dilute. So we can safely switch off. So put here no. Again, rescale it. And we can introduce one more thing, the polydispersity of the spheres. Because as we said, the polydispersity is never absolutely perfect. Then we have a way to put it here. And we can, here this, we can impose a, let's say 5% of polydispersity. So the curve is again more or less okay. So for the very end, or for the conclusion, so usually such quality of fits are accepted because it is almost never possible to make a fit which would absolutely or perfectly match the data. So the important that it reproduces the overall structure of the data, and that the parameters have the precision of around 5 or 10%. So this is already acceptable as an outcome in many cases. So this was a short training on the model fitting. I'm sorry if you couldn't do it all by yourself, but I think this was informative enough, like in this demonstration mode.
Yes, it was good.
Take my pardon, I have a question. Now, from all of these fitting procedures, can we say which is the maximal size of the particles, the minimal and the average one, and the fractions? For example, 80% belong to the maximal, 20% belong to the minimal. Can we obtain such kind of data?
Well, it's very hard. So there are a few approaches for that. For example, you fit the data by a histogram, in which all the sizes are present and all the sizes are varied. Usually this can be done by a Monte Carlo type of fitting procedure. From that you can obtain something. However, you cannot be sure because there are so many free parameters. But what usually we know for these systems, that they are made by a chemical synthesis, and the chemical synthesis usually produces a size distribution which is theoretically either a Gaussian one, which means a symmetric, or it's a log normal one, which is a nearly symmetric, at least for these big sizes. And if we use that kind of model, then of course from the fitting we can tell you that what is the maximum, minimum, and how they distribute. So we obtain a size distribution, but we assume that we have this type of size distribution.
Yes, thank you very much for your answer.
Just answering this last comment, you see there was in the chat a comment that interparticle distance is really small, but and so the structure factor should not be 1. But in fact, this Distance was in the electron microscopy picture, and this is not relevant because it is not the in situ. So it's not the same as in the small angle measurement. And such effects or artifacts usually happen if we try to get information from the microscopy. So then the sample is always modified. So I also thank you for the attention, and still, please, if you have still forces, then ask questions.